So let's start the class. I'm Praveen basically, and I'm from IIT Tirupati doing my PhD here. And I'm a PMRF scholar. So I'm working in federated learning with networks using these RL techniques. So I'm going to be a TA for this RL course. And the one thing I want that please make this session an interactive one so that you should also discuss it. I should also discuss with you the things. It shouldn't be one-way session. Let's make it two-way session so that you can ask the doubts. We can solve like coding problems and examples and get a more intuitive understanding about RL. So let's start the session. So I think week 1 is done by the professor. Am I correct? One of you can unmute your phone. Like, hello.
Hello.
Am I audible? First thing. So let's start with RL course. And one more thing, this is my mail ID which I'm writing. So if you have any doubt, like you can mail me also, like about the subject as well as this. Any research topic you want to discuss or about the RL things. So you can mail me. So let's start now. Today, we'll make the session as an introductory session only about what is RL and some like starting about these map techniques and all. CS is, it's small only, sure. Everything is small. So basically, let's start with like initial starting only. Like if I talk about traditional computer science, I'll start with very basics and then I'll build up and we'll go. What we used to do, we used to program computer for every task earlier. Traditionally. And now then we came up with the ML techniques. Like we are providing the example to the computer, which I can say that are the training set. And then machine is learning basically. To accomplish the task on the example. So what I'm saying is, earlier in the traditional computer science, we were like, we are feeding the computer, like you have to do this program. Then afterwards, we came up with the machine learning techniques where we are giving the examples that this is the labeled data. I'll come to supervised and supervised as well. These are the examples. This is the training set. We are training them and then the machine is learning by our like examples and then it is trying to like do the target thing. Or I can say when we are providing this testing data, then it is doing that. Basically, machine is learning to accomplish the task. Or if I can say, I'll give an image to the machine. Suppose I am feeding the images. Cat images. That this is the cat. Then, like lot of cat images, it will learn the pattern. In this data set also you can see it will learn the pattern from lot of images and then it will recognize that image if the cat image is given to you. So any idea which type of machine learning technique I'm talking about? Yes?
Clustering.
Yes. Clustering. Okay. Any other person? Deep learning. Okay. Anyone else?
Supervised learning.
Yes, yes. I'm talking about supervised learning. I'll come to the clustering as well. So yes, yes, Prashant. Yes, you're right. So this is basically the supervised learning. In supervised learning, we are given the labeled data. Labeled data means I'm giving the data. This is the input. This is the output. I'm giving the input as well as the output, and then I'm giving the testing data that you have to test that whether this input corresponds to that particular output only or not. Now, what is the supervised learning? Input is given, output is given. Can anyone tell me that what is the bottleneck or what is the limitation in supervised learning? Yes, come on. What can be the limitation? I told you that the images are fed up. We are giving the images, we are giving the output, that this is the input, this is the output. Then what can be the limitation in that? And then I'm giving you the testing data, labeling. Yes, anyone else? Lack of data? Yes, you all are correct. I have to give it more and more data. As more will be the data there, more will be the images, more will be the accuracy of that particular model. So I can say that we need lot of label data. That is the main bottleneck here. Got it? So what I'm doing basically, I come to this agent and all everything. I'm giving the input in the supervised learning, output, and I have output is also given and the target is here. And then I'm checking the error. But as you all told that basically we need to feed lots of data for this. That is basically a limitation in the supervised learning. This is basically a bottleneck here. Coming to the unsupervised learning. Now, can anyone tell me what is unsupervised learning and what is the difference between supervised and unsupervised?
Madam, in unsupervised learning, there is no target. We have only data, and from the data, we have to identify the patterns.
Yes, yes, you are absolutely correct. And some people have mentioned in the comments also, they are also correct that data is unlabeled, and you are also saying correct only that we don't have the target and we have to basically observe its behavior and observe the pattern of that. That is basically the unsupervised learning. Someone told about clustering also in the chat only. So is clustering an unsupervised learning? Yes. Yes. So basically, model is given. Yes, correct. So model is given the input data, not the target, or I can say the explicit output value. Here. So model has to discover the structure, or I can say the pattern. Yes. Any doubts? Any doubts? Please unmute your mic when you have any doubt. Otherwise, mute it. Okay, let's proceed. So basically, I was saying that model is given the input data, but it is not given the explicit output value. So model have to discover on its own the structure of the data. Any idea what can be the limitation in unsupervised learning? Yes. Now we are not saying that we are feeding with the output data is also given or so. We don't need output as well in this case. So what is the limitation in unsupervised learning? Unclear segregation of category. Okay, yes. Can you explain this point, Ashi Goel, like how unclear segregation of category?
Basically, we have to specify how many categories the data is to be divided in. For example, in K-means clustering. So it is unclear how many categories we should actually specify if we don't know anything about the data.
You are correct that if I'm saying about K-means clustering, then I have to mention what is the value of K, either if I'm taking 3 clusters or 2 clusters. What about DB scan clustering? Yes. Any idea? You're absolutely correct that there are clustering techniques in which we have to mention that this much, well, like K means clustering, K is equal to 3. We have to make 3 clusters. We are explicitly mentioning. Now, what about DB scan or the clustering? Any idea about that?
What if we don't know like how many clusters we want in our data and then just let the algorithm figure out, like maybe we can use some kind of measure like to analyze the clustering tendency and how good the clusters are. Then
Yes.
So
Yes,
like
yeah.
in that case, like we are not explicitly mentioning like how many clusters do we need.
Yes, yes, you're absolutely correct. And K means particular clustering we need, but we have other type of clustering in which we don't have to explicitly mention that.
Yeah, like DB scan.
Yes, yes. Now, can you tell me other limitation of unsupervised learning? Have you heard about concept drift, anyone? Yes. Ma'am, please, may I know what questions are we solving here? Actually, we are just, Shivam, we are just revising the topic and getting more intuitive way of, I'm explaining in more detail the things which you have studied in the professor's lecture. Or I'll solve the practice problems as we proceed, like coding questions and all. Okay. Okay, now can anyone tell me what is concept drift? Okay. So basically, this is the limitation, or I can say, which can come, concept drift can occur in unsupervised as well as the supervised learning as well. So sometimes the statistical properties changes over time. Or I can say input distribution also, it gets changed. Suppose, let me take an example and explain.
Ma'am,
Yes.
is it like a non-stationary problem like which sir was discussing in that video?
It's not non-state. Yeah, we can say that it's non-stationary, but concept drift is something it is not discussed in the lecture though. It is
Okay.
just like we are, suppose, let me take an example and I'll explain you. If you'll not get it, then we'll discuss about it.
Okay.
Like, suppose I have blog posts, blogs and all, and I'm clustering them. Now, if suppose new topics are coming and old topics are becoming less like popular. So with the cluster, which I can say now non-stationary because they are changing. Now the clusters which I have formed earlier, like from the old topics, now they may no longer be accurately like represent the data because they are changing. I can say the input data is changing here. So that is why the clusters are formed no longer are accurate. That is basically the concept drift. It is the related to machine learning. I can say the properties changes. If the properties are changing, the clustering is also changing, and it is no longer accurately representing the data. I can say.
Ma'am,
Though
it is like that the machine is forgetting the old data by getting updated with the new ones.
no, it's not like that. It's like I gave the data earlier, I clustered it. Now I'm using that old data only. I'm not updating it with the new data. It's like that.
Okay,
So,
ma'am.
ma'am, can like if I'm taking a new data, for example, if I'm streaming and maybe some new data are coming, and can it have like extra attributes? So can we also consider it as concept drift?
What can you
For example, like if I have a data which is identified by maybe 3 attributes, and now I am getting another data which is another like maybe another extra attribute. So is that also
yes,
considered here?
yes, because there is a
Okay.
change in data because a new attribute is added. Though if you want that, I can explain this concept drift topic. It's a huge topic. Like people are also doing research in this particular topic in the next class if you want. Just I'm giving you the gist of it so that you can get to know what are the limitations before jumping to reinforcement learning.
Okay.
So there are some questions also in the chat. So clusters will change with the changes in the statistical properties over time, like when the mean and variance changes, the equations to define the clustering change too. What I'm trying to say, if there is a new data coming, if there is a if the statistical properties, or as he said, that the attributes are changing, some variations there are with time, I can say, some attributes are changing, or some variations are there in the data, then the clustering like which we have done earlier is not now correct at this moment of time. That is basically the concept. Though if you want, I can explain this concept drift in detail in the next lecture. This is just...
Madam, just one philosophical question, since you're talking about concept drift. Basically, what it means is that concepts itself keep changing. Okay, that is one thing. And even the number of, there could be number of concepts which, because it's unsupervised, we don't know the target. It is just a bunch of numbers, bunch of attribute values, and what are the patterns, and there's so many concepts could be there. Okay, what the right concept, that is like groping in the dark, right? It is a very tough problem than a supervisor learning, right? And another thing, another hypothetical question. For example, we have a supervised learning problem. We have attributes, we have a target attribute. Okay. Suppose let us remove the feeling that that is a target. Target also we say that attribute 1, A1, A2, A3. Target also is A5. Okay. Mixed up the target also among the other feature variables. Okay. And now I want to pose this problem. I don't know what is the target, but there is a pattern here. There is a regression pattern here among these feature variables. Can unsupervised learning discover the regression pattern? Which variables influence which variable?
Yes.
I don't know. Huh?
Yes. Yeah. Unsupervised learning is mainly because that we don't have output, we don't have the target variables, and there are patterns like which are coming. Then unsupervised plays the role in making the patterns together. That is what where we do clustering there. That same patterns are clustered together. You got the answer?
Okay, I got it. But it need not be clustering. I was looking for some regression pattern, some variables affecting the other variables, which is causing.
Yes, yes. It can
Yeah.
also be regression there. That one variable is dependent on the other there.
Yeah, yeah. Okay. So that means unsupervised is a more tougher and computationally more challenging than supervised, right? Technically.
Yes, yes,
Yeah.
yes, yes.
Okay, thank you, madam.
Okay.
Ma'am, that means in a whole that the clustering properties are only changing with the addition of new data only, correct?
Yes. What
Ma'am,
I'm
I was
saying, concept drift is like we are changing some properties. Some properties are changing in the data in future, like some blog or something. We are taking the example, like now new blogs are coming. The old one may not be the accurate one because the new data is coming. An example, like the example which I am taking is, suppose there are the posts, blog posts there. Now new topics are coming, old topics are becoming less popular. So clusters which were formed initially, they may not give us the accurate data, or they cannot represent clustering in better way because they are not accurate. That is made of the old data. Now the properties are changed. So that is why, as the properties are changed, that is what I'm trying to say, that is the concept drift, that the statistical properties of the input distribution itself are changed. That is what is the limitation in the unsupervised learning.
okay, ma'am.
So now let's proceed to RL, our main topic here. So if you want in detail, then we can discuss in the next lecture as well. I'll come up with the more examples of the concept drift. So we can discuss at the end of the lecture about this. So now we come with the reinforcement learning. Any idea what is reinforcement learning? Simple question.
Learning which is like guided by reinforcements or rewards.
Okay.
Learning by experiment means trying it out and getting the feedback and then learning. So yeah,
Yes.
in one way I look at it, for example, in supervised learning, we have the entire data in one go, one set, a huge data set we get. But in reinforcement learning, every iteration we get a data. So data comes in sequentially by experimenting, by trying. So it is not in one go. For example, the main difference I see from your description of supervised learning is, in supervised learning, the 1 million items, okay. But in reinforcement learning, 1 million times we have to repeat. Maybe I don't know. That's how I think. Yeah.
Okay. Yes,
Here,
basically.
yeah, here learning is continuous. In supervised learning is one shot. Only,
Yes.
right.
So basically, we are interacting with the environment, or as all of you have written, learning from trial and error. An agent learns from rewards and punishment. Agent learns based on rewards. It receives based on actions. Learning by feedbacks, learning from experiment. Yes, you all are absolutely correct. I can say reinforcement learning, trial and error learning, a sequential learning as well, as we told, and learning by feedback as well, learning by rewards, or learning by punishment. Okay, there was professor also discussed about cycling. So is cycling unsupervised, supervised, or reinforcement learning?
Reinforcement learning.
Reinforcement learning, ma'am.
Why it's not a unsupervised learning? Because we
Because the
can't.
subject itself has to figure out how
Ma'am,
it has to cycle, and with interacting with the environment. So the rewards are basically you have to balance yourself, and if you fall down, then that's a negative reinforcement.
Yes, yes. So
Ma'am,
basically,
this is because it is not an unsupervised learning because we are not looking into 1,000 cycling videos to learn cycle.
yes, you are absolutely correct. You both are correct. And someone has replied in unsupervised, there are no reports. Yes. With cycling, we can't see the videos. We can't see the videos, watch the videos and learn. We can't identify the patterns. Okay, this is the way we have to cycle. Or you said that we can't say that this is the way we have to balance. Basically, we have to try it on our own and we'll get the reward or we'll get the punishment by falling and then we'll learn it. So that is why cycling is basically reinforcement learning with the negative feedbacks as well as the positive feedback. Basically, reinforcement learning is inspired by the behavioral system. As in the lecture also, Pavlov's dog experiment, the example was given that when you ring, no, our supervised, there is a question in the chat, ask unsupervised and supervised learning, no. I'll cover from the basics. Supervised and unsupervised learning will not do. We'll only focus on this reinforcement learning just to give the basic idea. Then that's why I introduced that. So, I'll ring, if you'll ring the bell and serve the food, then basically the dog basically comes and eat. You'll do it every time, and after the number of times when you ring the bell, the dog automatically will keep start salivating because it know that you're going to give the food. That is basically the behavioral psychology that dog gets to know after ringing the bell that food is going to be given. So here, what is the reward? So now let's come to the terminologies. The Pavlov dog example, what is the reward?
Food.
Yes, food.
Ma'am, food was the reward.
Okay, and what is the input which is given?
The sound of the bell.
Ringing of bell.
Yes, yes. So basically, reinforcement learning, I can say that it is learning from the rewards as well as the punishments in the absence of any detailed supervision, unlike supervised learning. Now, what do you mean by delayed rewards?
That the rewards we get are really not instantaneous, and we are making decisions which will impact in the future. So by delaying the rewards, we are actually waiting for the agent to figure out a good, nice way, which is not only not to maximize the reward at this current instant of time, but to look into the future so that we can make a proper step. I guess.
Correct. And if I say that you are getting a delayed reward, you are saying in the perspective of we don't have to see the immediate reward, we have to see the future perspective also. You are saying in that
Yeah.
Now what I'm saying is when you get the delayed reward, an example, when you're not getting the reward immediately and when you're getting the reward, your reward is getting delayed.
Like in a game of chess, it doesn't matter if we are losing a piece now, the actual reward comes in the end, whether we win or lose. So the rewards are delayed in this case.
Yes. Or I can say that if you take a particular move in the chess, because of that move, you are losing the game, but you will not lose at that particular moment. Your reward, I can say the cost you'll get at the end that you are losing. It's not that we are losing at that, we are losing because of our last move. We are losing because of the 4-5 moves before which we have taken. Can I say that that is a delayed reward?
Yes, ma'am.
Or I can say in the cycling also, if there is a stone there and you are cycling there, and then you're going to fall because of that stone, but still you try to balance for 1-2 seconds and then fall down. It's not because of that last second you fall, you fell down because of that stone which was before 2-3 seconds. So that is how you're getting that delayed reward. Or I can say the reward is a cost also. Cost is basically the negative reward or the punishment here.
Madam, I would interpret this way. If I try to compare supervised and reinforcement, in reinforcement, there is no concept of a reward for any state, actually speaking. The reward comes only after action, and action is timed. So obviously, when you are in any state, there is no meaning of reward. You have to take an action, then only you get reward. The action is take a time step T, and after that only you get. So that's why you call it delayed reward.
You are correct that after taking an action, we are getting the reward. Delay, always you'll get the reward after taking an action.
After taking, that's why it's called delayed reward. So
carry
just
on.
by being in the state doesn't actually, there is no reward. That there is no meaning of reward, right? If I just stood still, okay. So there is no meaning of reward. The reward is if I perform some action, and that action takes time, and time means delay.
Okay, let me give you one more example, then tell me. Okay, I'm in the chess game. And I took some move. This is the action by me, and I lose or win after that move. Okay, let's not take this example. Some other example. Okay.
What if an agent is supposed to just punch the boxing bag in the club? Then it's not delayed at all. Like we are supposed to get the instantaneous reward. Yeah,
That is
so
what I'm trying to explain. That if you are in the particular state and you take an action and instantaneously you are getting the reward, that is not immediate reward. That is basically we are getting the reward at that particular reward. We'll always get after the action only. We'll not get in the particular state. We'll be in a particular state. We'll take an action. We'll get the reward. This is how it will be. Now, if we'll get at that particular time only, that is called as immediate reward. If after this action, we are going to another state, and then taking action, and this process is going on, and then you are getting the reward because of this action, this particular action, not because of this last action. Because of the action which you have taken 2-3 steps before, you are getting that reward. That is basically a delayed reward. What, like in the chess move, you take the second move, you take the third, fourth, fifth. This second move which you take was the wrong one. That is why you lost. Because of this. Any doubts? No. Don't have any doubt, please mute. Now understood this concept of delayed and immediate reward?
Yes, ma'am.
Okay. Now coming to, we discussed about this. Coming to the policy. Yeah, what is policy? Any idea what is policy? Please mute it.
It's a sequence of actions or plan, like how we sequence, or like what are the sequence of actions which an agent is going to take in order to like attain a certain goal, maybe.
You're correct. What actions we have to take, or I can say the rules, or when we are at a particular state, what action we have to take, as you told.
Yeah, the state as the input and what actions we can take in that state. If we are able to define it for all the states, then that is a policy.
Yes, you're correct. Okay, someone is asking, can a move in chess have both immediate and delayed reward? Okay, if the last move, suppose I'm taking a move and I lost the game. Last move and I lost the game, that is immediate reward. That was my last move, was the incorrect move, I can say. Delayed reward in the chess is, I took the move, after some time I lost because of the move which I have taken before some time. That is basically the delayed reward. Got it, Rahul? Okay, let's proceed. So we discussed about the policy as well. Now, coming to what is stochastic? As professor has also used the word stochastic environment. What is the stochastic?
That which is very
I'm getting
noisy.
no reward for an action.
The uncertainty in the environments where there is randomness.
You all are correct.
Madam, this is where some confusion. See, a stochastic policy means at any state, what are the possible actions we can take? That is random. We don't know. That is defined by some distribution. If it is for every state, there is an action, there is a table kind of thing, yes to A, yes to A, very predefined mapping, then that is deterministic. And at every state, we cannot define precisely what actions, but we can define some kind of random distribution, then that is stochastic.
Yes, you are correct. Basically, in real meaning, stochastic means random, and you told about in the context of this stochastic policy and all. You are correct here.
Just a minute, madam. Here only I'm getting confusion. The objective of the reinforcement learning is the overall objective. Forget about this course. The overall objective of reinforcement learning is to find the best policy, right?
Yes.
Correct. But
yes.
Is the best policy distribution the stochastic distribution finding or a deterministic distribution? Is only one table, yes to A. For example, we have 100 states, and for every state there may be 10 actions, let us say. So the final goal of reinforcement learning is a deterministic table or stochastic table, yes to A, or is very precisely for every state there is one optimal action, for every state. Is it like that, or
it can be both ways? Like, it depends on the environment. When we solve the problems, I'll get to both of these things. This is just the gist I'm giving. We'll get to both stochastic policy as well as the deterministic policy. It depends on which problem we are solving and which environment which we are solving. What is the environment in that problem? So we'll get detail. Don't worry, we'll get in detail. This is just
okay, ma'am.
Okay. So now coming to just discussing some. What is exploration and what is exploitation?
Exploration is like looking into all other like types of actions, and exploration is just like being greedy and maybe just selecting an action which is based on our overall knowledge, and exploration just demands us to expand what we have already seen.
Yes. Okay. An example?
Okay. So okay, like if there is a bird which wants to find food, like it knows that there is a place where it gets food daily. So it's like using its previous knowledge to find the certain location and get the food, but it has not explored the overall area. So it has not explored. So if it explores, then it might find some better solutions, better places where it can accumulate much more food. So
Yeah. So exploration versus exploitation. Exploitation is we are approaching greedily towards one thing only, as he told. If suppose a bird wants to find the food, bird is going to one place only, so that because the bird knows that I'll get the food from here. But bird is not exploring the other places from which the bird can get more food from the other places. So that is why we have to keep the balance between exploration versus exploitation. We have to exploit. I know this is the best one. I have to go there. That is exploitation. I'm exploiting. But I also have to explore the other ways from which maybe I can get the better reward. So this is the difference between the exploration versus the exploitation. I hope that you got these policy. What is policy? The rules basically. What are rewards? You have got these terms. I think I don't have to repeat this. What is stochastic environment? Now coming to tic-tac-toe example. So suppose that there are two players in tic-tac-toe. So one player is doing the cross one player is doing the zeros one. So let us ask from you only. So what is the tic-tac-toe? How RL is doing it? Rather than me explaining. Yes.
So there is a 9x9, like, 3x3 grid, and like each player will have at most 4 moves to win. So
4 or 5.
yeah, 4 or 5, yeah,
Mhm.
5, yeah, I guess. So then the player,
Yes, carry on.
yeah, so for winning, like at least like either horizontally or vertically or diagonally, either of the one like symbol need to match. So who like and the player take turns alternatively. So whoever like finds the way horizontally, vertically, or diagonally, then he or she wins, I guess.
That is basically tic-tac-toe. Now, how RL, we are going to do that RL in this RL. Basically, we can do how we can learn. Now, suppose we are saying that we are making the computer learn what is or how to play this tic-tac-toe. So, how can we make them learn? So, let us take that the opponent is the weak one. Why opponent is the weak one? Okay, why opponent the weak one? Why we are assuming that opponent is the weak one?
Because
Ma'am,
if the
so that
opponent
we
is
can
very,
get a reward.
From the start, then
Okay.
there may not be a chance for the agent to learn because it will keep losing.
You're not audible clearly. Can you repeat?
I was saying that, am I audible now?
Yes.
If the agent is playing optimally from the start, that is the opposite player,
Hmm.
then the agent may not learn because the opposite player will keep on winning, so it won't get rewards. So it will keep on taking random moves in the beginning at least.
Yes. So if the opponent is also, we are assuming that opponent is also stronger one, so agent will not win initially, or it will be a draw. Through that, agent will not learn which position is the best one. So we are assuming here that the opponent is the weaker one. So now what we are doing is, we are putting the cross in all position and checking which is having the highest probability. I'll explain more detail. What I mean by that is, suppose I take two methods here. One is that player game to the end. Player game to the end means we'll play the game to the end. We'll keep the trajectory where I'm keeping that, like cross or cross and the other thing. So where I'm placing that particular cross, and then I'm going till the end of that game, and then updating the states where I saw that I win. Suppose I win that game, then I'll update the probability. I'll increase that probability of winning. Suppose keep it here, and then here. I win it. Someone keep it here. So what I am doing is, when I win it, I'll increase the probability. That the first probability, when I kept it for the first time here, the probability was suppose 0.3, I'll increase it to 0.4. I'll go back and I'll increase the probability. Okay, when I place the first cross here, I'll win it. So I'll backtrack it and I'll increase the probability. Or suppose I come to the end and I basically lost the game, I'll go back and I'll decrease the probability of the winning. Okay, I don't have to place the first cross here. Because when I put the first cross there, I was losing at that game. The other alternative is, I'll play multiple games, keep the history of all the games, and whichever the game I win, I'll compute the probability. Like whichever the game I'll win, I'll update the probability of that game's win. in which state I have gone. State means the particular position here. Got the concept?
Yes, ma'am.
Any doubts?
Ma'am, is these two kinds of learning is preferred according to the situation based, or the system prefers any one of the method in all of the conditions?
You can prefer both of them. This is basically alternative approach.
Madam, just one question. The second option, if you keep history of all games, that means history of the patterns of the sequence. We can even convert that into supervised learning, right?
Supervised learning is we are given the input data. Here we have to work, we'll get the feedback from the environment, then we'll make. This is not like data is, we are working. From the initial step, we don't have any data. We
See,
don't have,
no, since you said in history, let us say we played 1,000 times. So 1,000 times, the target level is win, lose is there. But the variables, the feature variables are the patterns. Sequence of patterns. So I can convert that into supervisor also.
that is after playing the game, after you are getting the feedback from the environment.
Yes.
Then that is the same thing, because what we are doing is we are interacting with the environment, we are getting the feedback, then we can make a lookup table, input, output, what is the state, what is the action. And then we can say, like, when we are in this particular state, we have to take this action.
Ma'am, I have a question, like not a question, just a doubt. So like is reinforcement learning actually helping us to like abstract out the complexity of the whole environment with rewards?
I can say in some situations it is more computationally expensive also, it is more complex also. But
Oh, okay.
more like we'll get in more detail about this. Like there are two types of approaches. One is this lookup table. Obviously it is very, if you think also that keeping the history and all, it is not actually possible if this is just tic-tac-toe. If I talk about the other things, this is just, as you said, 4 to 5 moves are there and total 9 states are there. But if we talk about the other things, we'll have so many states and action. So it becomes computationally very expensive to maintain the lookup tables and all. So then we'll come up with some other approaches that is model free also. And TD learning, I'll explain in the further classes what are these jargons I'm using, this model based, model free.
Also, ma'am, the thing is that, for example, if I have a very partially observable environment where, like, if I use supervised learning, so for that stuff, then I have to actually find a way in which, like, I have to find out all the hidden or the latent variables which contribute to the working of the whole agent, or like how the agent moves in that particular environment. But in that case, reinforcement learning, like, we can abstract it out, like, by rewards and stuffs. Is it like, am I thinking it correctly, or like?
Yes.
Okay.
And as you are thinking that partially observable environment, we'll get to more in detail about like POM, DP and all, partial observable Markov decision process. These environments and all we'll talk about in detail in the next like.
Okay. Thank you.
So now coming to temporal difference or temporal TD learning, I can say. Just write TD learning here. Any idea what is TD learning?
We are assuming that the rewards we get at the later stage T+1 are more reliable than the rewards we get at T stage.
Yes, you're absolutely correct. That the rewards that we get at T+1, we can rely on that more than what we get in T. Because we now at time T+1, we are in more better stage, or we have learned more about that state particularly. So the rewards which we get in T+1, they are more reliable than the T stage. Now, going to tell you something.
Madam, this
Hmm.
TD learning and the delayed learning is the same concept, right?
Which one? Deep learning and
Delayed,
Data.
delayed rewards.
delayed rewards, and I'm not getting the other thing.
TD learning.
No. TD is basically, it is, we are getting the reward not after particular movement. I'm taking a state and I'm going to a particular action. After that, taking an action basically, and then I'm not getting the reward at that particular moment. I'm getting the reward after some time, that is delayed. Now talking about TD learning is basically that if I'm in a particular time T, I'll get more information at particular time T plus 1 than T. That is what is TD learning. That you have more information, you can rely on the state T or on the reward T plus 1 more than T basically. That is why we were saying that, okay, I'll tell you this example here. I'm in a particular state point, supposing this tic-tac-toe only, this going to this state, the probability is 0.6. When I went to the next state, the probability is basically at time T plus 1, the probability is basically 0.3 here. So, which means that I have to T plus 1, I have to reduce the probability of this also to 0.5 or 0.4 basically, because when I went to T plus 1, I get to know the probability which I was taking, that's 0.6, that is not the correct, because the probability is reducing here. So I'm basically decreasing the probability of the previous step. So
Yeah, madam, this reminds me of back propagation in neural networks. Similar concept, right? When you go and then start updating the previous.
This is basically backtracking only. I can say that when going and then we are coming back and back tracing it, and then we are increasing the probability or reducing the probability. And now we come with the exploration, and here also, as I told you, what is exploration and exploitation. Here also we can do the exploration as well as the exploitation. We have to balance between them. That also we'll discuss, like how to balance between exploration as well as the exploitation techniques in the map thing. Like we'll come to know about greedy, epsilon greedy, how they are basically balancing them, and get in more detail about that. Now coming to immediate RL. As we have discussed, what is immediate RL? When we are getting the reward at that particular moment only, when we are taking the state, when we are at a particular state taking the action, and that moment only we are getting the reward after taking the action, that is the immediate RL. And here we are not talking about the states here. Suppose, okay, let's not talk about states here. Yeah, the professor also took one example of drug here, that I have drug 1, drug 2, which is given to microorganisms here. So these are the arms or actions. You got to know about the terminologies, what is state, what is action, what is reward and policy, everything is clear now. Because that we'll use. So now I'm, okay. So what we are saying, now I'm not taking any state here in this. Now I have 2 drugs, suppose, or let us take other example. Okay. That will be of exploration only. Suppose, let's take an example. I went to hotel 1 to eat, or restaurant 1 to eat, and restaurant 2 to eat. Suppose this is the example which I'm taking of exploration and exploitation only. Suppose here the cook was absent at that day, and I didn't like the food here. Now I went to the other hotel and the food was good. Now I'm saying that I'll never go to this hotel. I was unaware that cook is absent here. So basically I'm not exploring more there. So we have to, that is what we have to maintain the balance between exploration and exploitation. That is the main thing. And the other thing, immediate RL we have done. This is, and then coming to bandit thing. Any idea what is bandit? What is map? Multi-arm bandit?
Basically at the casinos, the machines which you have, like you pull the lever and you get the points.
Yes.
Like we pull the lever and there are times when like you hit the jackpot and like all the 3 matches and you like earn the whole money. But in order to get there, like you might have to play a lot of times. You have to put your own money in the slot. So that's why it actually steals your own money. So in that way, it's a bandit, I guess.
Basically, we are pulling the arm. Like as you said, we are pulling a lever, and then you are getting a reward. You are getting a jackpot, or you are getting a you are losing your own money. I can say that is the cost here. So basically, we are having the arms here: arm 1, arm 2, arm 3, and so on. And then we are pulling an arm. So either we are winning or we are losing here. Like winning or losing, I mean to say, suppose I pull that arm, pull arm 1. Which arm should I pull, which will give me the more reward here? Suppose now this exploitation comes. Suppose this is giving me the good reward. It doesn't mean that I'll always put that, pull that arm. I'll be greedy in that. I have to pull other arms as well so that I can maintain the balance there. So basically, multi-arm bandit, we have the multiple arms, and I have to pull the one arm, which will give me the better reward.
Ma'am, that means eventually to get a reward, I have to suffer some kind of punishment.
You can say that to get the reward, we have to explore somewhat so that we can get the best arm. I'll come to that regret thing now only. Then I'll ask your question.
Madam, just one more.
Yes.
Yeah, madam, one more question. See, hypothetically, if all the arms of the same type, same distribution, same thing, then it doesn't matter, right? If you keep on exploiting also same thing, everything is the same. Exploiting also same thing.
Then you can pull any arm, all will give the equal reward there. Then
Yeah,
it does.
What I mean is, even if it don't exploit, even if we keep on pulling the same arm or randomly pulling any of the arm, it doesn't matter. All are same.
If all the arms are equally only, they are giving equal reward only, then it doesn't matter whichever arm you pull.
Yes, yes. Okay, I got it.
But ma'am, the thing is that when we are playing that game, the thing is that all the arms actually look similar to us. So for like everyone thinks that like anything is random, right? So it does. So also the thing is that if you think about the reward is not evenly distributed. Like it only occurs at a certain instant of time. We might think that it's a poison, distributed in a poison manner. So in that case, like I guess.
Yes.
So the question does not arise, right? Like how the arm could be similar.
Yes. He was giving an hypothetical situation when the rewards are all equal for each of the arms. In actual real scenario, it cannot be possible that all the arms will give equal reward, or if it is so, then it doesn't matter, then it is not a matter.
Madam, I'm not saying that equal reward, the distribution, the probability distribution, the randomness of rewards of each machine is identical machines. Okay. Whatever uniform distribution we have one machine, the mean and variance, mean and standard deviation, if exactly identical to all the arms, that is what I'm talking. So every time you pull, we might get a different reward based on the distribution, normal distribution. But
yes, carry on.
Yeah, but all the machines are exactly carbon copy of the same one. Then it doesn't matter if you resort to one machine, keep on pulling, or randomly picking 10 machines, and also it is the same. That's what I'm saying. Right.
But the thing is that the reward is happening at some kind of instant, right? It's not like the thing is that you can all the slot machines are really like if you think about it, it's made by the same brand, then it's actually like the same copies only. But the way the reward is working is like it's not happening at some intervals of time. It's coming at some kind of a weird instant of time. So you can just say that like the variation really will make this thing. Like, does it really matter though? Like,
No, what I'm saying is that vagueness and randomness is common across all the machines. Basically, in a statistical language, we call the randomness as a probability distribution. Okay, I am saying the probability distribution of a mean and standard deviation is exactly identical. So the all the machines are so yeah. But the assumption actually the sir told us is that the casino won't keep the same machine. Some machines sometimes very rarely give, some machines frequently give. They all mixed up, and no one knows the actual distribution. Okay, if we know the probability distribution podcast for each of these machines, then exactly we go to that machine and do it. So obviously they mix up. Nobody knows the distribution. That's why people try randomly exploring and exploiting.
You both got your answers, or I can explain. Any doubts?
yes, ma'am, sure.
You got your answer, or I can explain like.
Oh, ma'am, you can explain.
So basically, what we are saying is that we are having the scenario in which we are getting the different rewards for that, for every arm. So if we are getting the different rewards for every arm, it means that the one is the best one than the other. If all are giving the equal rewards, then there is no case of this multi-arm vendor. Then you can randomly choose any of the arm. Am I correct?
Yes, ma'am.
So now coming to the properties, what is asymptotic correctness? Yes. Come on.
Eventually at as time approaches infinity, like we will figure out.
Please mute your. Yes, carry on.
So as time approaches infinity, so we'll eventually figure out which arm, like by pulling which arm, we can maximize the reward.
So
how do we figure out, madam? How say as time approaches, that means infinitely we keep on pulling randomly any of the arm. How does it approach?
What we are saying that as time approaches infinity means that if we try to do it again and again, then we always come to an optimal arm. Basically, we'll always choose an optimal arm which will give the best reward.
So that means after every attempt, one round, for example, let us say there is 10 machines. So first we explore all the 10 machines, then find the best one, and like that.
I'll explain about that techniques, how to explore, how to exploit by greedy, epsilon greedy, Thompson sampling.
No. What I want you to explain, madam, is how asymptotic correctness. Can you explain the experiment? Yeah.
And they are not. This is basically a theoretical approach. What they are saying is when we try to many times when we try to. Can you mute
on, guys?
Wait a second, please mute if you don't have any doubts. Okay. Now what I'm saying is when we are basically choosing the arm multiple times, or we are running it infinitely, as we said that we are doing the same experiment multiple of times, then we get to a point where that arm will always have the highest payoff, or that arm will always get the best reward. We give that guarantee that we will select an arm which has the highest reward there. That is basically, it is basically a theoretical approach. It is not, I can say, the practical thing. Though this is These are all very vast areas, the pack optimality and regress.
No, I got it, madam. Where I am trying to do is, let us say there are 10 machines are there. I pick one machine. I do infinitely number of times I pull. Then I go to second machine. Infinite.
No, it's not like that. It's not like that. We are saying we are having the 10 machines. We are running the experiment. We are pulling any of the arm. We are exploring. We are exploiting both of the things which we are doing. After a point, we'll reach to the point. Like when there are, like we'll give you a guarantee that this arm is basically giving me the highest reward.
Oh, we have to explore and exploit infinite times. Yeah.
Yes.
Right. Okay, I got it.
Basically, we are not putting any bounds on you. We are no bounds on you, and it gives the guarantee that you will select an arm which has highest payoff or reward, I can say.
Okay, madam, I got it. Because it is infinite, which is not profitable, we find the optimal one using that epsilon pack or something, right? Correct. This is a compromise. So without going to infinite, how to find the best arm? So that is the model we are going to suggest, right? Pack optimality, correct? Yeah.
That will go in detail afterwards.
Okay, madam.
Ma'am, then what is the fundamental difference between the bandit learning and the asymptotic correctness?
Bandit is basically, it is the solution only. What we are saying bandit is we are having the arms, which one is the best arm? That is basically bandit. Now we are giving the guarantee that this is when, okay, what I'm saying is I have arm 1, arm 2 till arm 10. Now I'm saying that arm 3 is the best one. I did some bandit approach, some mad approach, like greedy or epsilon greedy, or I can say epsilon greedy approach. I did something. Now I said that arm 3 is the best one. Now, is it asymptotically correct that arm 3 is best one? What do I mean
So
by that?
because we have explored only a one machine.
No. Suppose I have done it. I have done my experiment. I have explored, exploited. I have done the algorithm. I have run it multiple times, and I get to know arm 3 is best one. So now, is it asymptotic correct that arm 3 is the asymptotic? Like I can say that it is asymptotic correct or not? That arm 3 is best one. What do I mean by that? Any idea?
So like we have performed like lot of experiments, and according to our observation, like with arm 3, we are getting like the best reward possible. So this does conclude that we are actually reaching that we are not actually getting the highest payoff for the like the total payoff, but the reward which you're getting is actually significantly better than what we could actually possibly accumulate from pulling other arms.
Now what I'm saying is I did some math. Forget about asymptotic correct for a second. Now I'm saying is I did some math thing. I exploited some greedy approach or any approach I did, and I came to a conclusion that arm 3 is the best one. Now I'm asking question that is it asymptotically correct to say that arm 3 is the best one? What do I mean? I mean, yes, come on.
Yes, madam. Provided we do it many times and then make a conclusion that arm 3 is correct, then we can say it is asymptotically correct.
Okay. Anyone?
Maybe we can give a probability that with this probability it will be asymptotically correct.
Okay, what do you mean by giving the probability? With this probability, it is asymptotically correct?
Ma'am, maybe we can give a bound on the probability that with a probability greater than equal to 1 minus delta, it will be asymptotically correct, or maybe within a certain distance.
You are talking about pack bounds here. Am I correct?
Yes, ma'am.
What I'm saying is let's not take any bound. What I'm saying, like suppose I did, yes, you are almost correct here. I did some Thompson sampling or any approach. I said that this is the best one. Now, to say that it is asymptotically correct, I means how many times I'll run the experiment, infinite times I'll run the experiment, always arm 3 will give me the highest payoff. Which means that yes, this is when every time, like after I have chosen this arm 3 as the best one by some approach, asymptotic correctness means how many times you'll not put any bounds that give you a guarantee that the selected arm will always give you the highest reward. Got
Ma'am,
it?
this means that in asymptotic correctness, we perform huge amount of experimentation, while in bandit learning, we do some kind of means limited experimentation to get our probable result.
Actually, it is a solution. We are saying that it is not that bandit is different or asymptotic correct is different. It's not like that. It is a solution. If I'm doing some map thing, then we are checking that whether the arm C which we are selecting it is good one, or whether it is how much regret it is giving, with how much confidence we can say these all things we are checking after doing this map. This is only the solution of the map. We are doing only map thing. This is the theoretical properties. This is theory that when that how much like I got this arm map is done. Now what we have done in map. Now what we are saying that this arm which we have selected, is it asymptotically correct or not?
Yes.
Got it? Any doubts? Yes. Any doubts?
Ma'am, so the bandit learning gives us the gives the solution based approach, and asymptotic will give me about lot of experimentations.
No, that is what I'm saying. They are not at all different. We are talking about bandit only. We are talking about map techniques only. What we are saying that is that the arm which we have selected, this is a solution of map. Is the arm which we have selected, is it, we are asking the question to us, what what we have done in the map, whatever the arm we have selected, is it asymptotically correct? Is it giving me that much of error? Is it giving me that much of regret? That is the questions we are asking. We are applying only map techniques here.
Okay, ma'am. Okay, ma'am. Got it.
Got it? Any
Yes,
other doubts? No. Okay. Asymptotic correction is the solution of bandit problem. Right. You're right, Shaurya. Okay. Now coming to regret optimality. Yes. What is regret? Okay, let me. Yes, first step.
So the
Regret
difference.
is the total.
Yes.
That is all the times we didn't get the optimal output. We lost some potential amount of reward.
Yes, you're right. Anyone else who want to give the answer? Someone else was also speaking. Yes.
Man, the same thing, like the total, like what we could have accumulated, the best possible reward, and what we have actually accumulated, the cumulative sum of the rewards. So if we just subtract it out, so the area under the curve, yeah. So we'll have the regret.
But
So
but madam, we don't know the best possible reward, right? How do we compute the regret?
Yes, I'm coming to that. This is a hypothetical situation in which we are saying, yes, there are ways, I'll tell you afterwards. Now we are assuming, or in the next class, let us code regret only. I'll show you the code. Now what we are saying is, we are assuming that, suppose from the time 0, I know that this is the best term. This one is the best term. Basically, this is the reward I'm getting. I know that from the time 0. Yes, you are right, absolutely right. We don't know actually, if we think practically, we don't know that this is the best arm at the starting, because we are trying it from the math techniques, or we are exploring it, exploiting it. From the starting, we can't know this is the best arm. So let us take an hypothetical situation. Okay, this is the best arm is giving that much of reward. Okay, and then I'll tell you how we used to do in our research, how we plot this regret and all. So from the time 0, we are doing this. So what we are doing now, we are doing, now let us say this is the best arm giving the reward. Now we are exploring as well as exploiting and reaching closer to reaching closer to this best one. So this portion, basically, this is the regret, that what we are losing in that. So we are now, suppose, let us say that this regret is smaller one. Is there any difference?
Yes, ma'am. The starting slope is actually like really less. So like it became greedy, but the thing is that it didn't quite explode properly. So the amount, so the possible highest possible reward which it got after selecting is significantly less than what could have got after exploring.
You are right that. Suppose I have explored less. If I have explored less, then I'll be lesser close to the optimality. If I have explored more, though the regret will be initially in the starting, it will be more, but after that, I'll be very close to the optimal situation. Am I correct? Anyone having the doubt in this?
No, ma'am.
And if we want to calculate the regret, we can do that after performing the experiment only. After performing the experiment, we will get an idea of what the optimal arm was. And if we keep a track of our previous rewards, so maybe then we can calculate the total regret.
Okay, okay. What is this then?
Ma'am, this is getting closer to the optimal reward.
This is after experiment.
Yes, ma'am.
Then what is this?
Yes, ma'am. As the experiment goes on, basically, after a lot of experiments, we can keep a track of previous observations.
Okay, so you are saying that we are performing an experiment and we got to know this plot. And
Yes,
then what about this plot? What you are saying that? The best one?
then we can probably estimate in which direction it is
So,
approaching to.
The experiment which you are performing is an optimal one?
Then we are basically making an assumption that we are eventually approaching the optimal arm.
Yes.
Madam, as I understand it, for example, in a scenario where we are doing less exploration, maybe the curve will flatten out much earlier, much below the desired performance and plateaus out. In contrast, if you are exploring much more, then there is a high chance of reaching that invisible or unknown plateau much higher. Is it right?
Yes, you are correct. Absolutely correct. Yes, Ashi, you were saying something like we are doing the experiments. We are getting to know this curve, this one. And then you were saying that by the experiments only we are getting to know this. Then what is the difference between the above and below? You are approaching right only. Yes, yes, come on.
Yes, ma'am. Then in the below experiment, we actually didn't explore the right amount. So our estimate of regret will be a bit off because we guessed the optimal arm wrongly.
So you went back and you did it again. Then why to check you have done this only. Then why to check this one? Usually when we do this, why we have to if you know the optimal one, then why you are doing this experiments only? Then you'll say, okay, this is the correct.
No, ma'am. I'm not saying that we will know from the start what the optimal arm would be. I was just saying that after a lot of experiments, we can probably say that we are approaching the correct arm because of asymptotic correctness. Then maybe then we can estimate the total regret we accumulated along the way.
Yes. Suppose there are approaches of optimal approaches like NDP or so, though they contain states and all, that is not a mad approach, but still, like we have some optimal approaches. So what we try to do is, I'll tell you about this. Model based, I'll not go in detail, I'll just say, or I'll not mention these words, otherwise you'll get confused. We use this regret when we have this optimal approach. There are some optimal approaches where we'll get the result as optimal only, but there is a limitation. So can you tell me, or anyone else, like can anyone tell me that what can be the limitation with these optimal approaches? What can we face?
Ma'am, can you explain the situation again?
Okay, what is there? Like this is basically the optimal approach. This line, this one. So now what we are trying to say is that we have some RL techniques which we'll get in which we are sure that we'll get the optimal approach or optimal results or optimal reward at the end. And then actually she was asking, or like students are asking, like how we'll plot this regret plot. So we'll get the optimal approach, but there are limitations in that getting that optimal approach. Any idea? We studied now only. What can be the limitations? Try to think.
Ma'am, the limitation could be that we could apply optimal approach to a limited number of experiments only, which we have performed earlier, but we cannot apply it on an unknown experimentation or unknown situation.
No, we have states, we have actions, we are applying it, we are getting the optimal.
It would take a lot of time.
Yes, it will take a lot of time. It is computationally very expensive. It will take a lot of space as well. So sometimes in our experiments, we have optimal approach. We plot it here. Then we are saying we are coming up with the suboptimal approach. We are exploring and exploiting and then checking that what is the regret between there. But this is basically less computationally expensive, taking lesser time, and saying we are saying that this is the more better one because we need lesser time to do that and we don't want to waste much space. So then we are plotting this regret plot and saying that we are very closer to this optimal one in the in our researches, like we are very closer to the optimal one. So let's go with this approach rather than going with the optimal approach. So mainly in the research, this is used like this, and that is what I'm trying to tell you about how this regret plots, why this is needed, and all of these in the research.
Madam, you know where I am. My head is turning is like a chicken and egg. First, we have to discover that optimal reward, right? That optimal one. Only after you discover, then we say that where we stop or no.
No, it's not like that. It is just that they are asking that how can we use this regret. It is not, we always, there are situations in this in which we are getting the optimal approach because we are having lesser state space. So it's fine to have that optimal approach. It will not take that much of time because we are having lesser state space. Let's take tic-tac-toe only, 9 states and all. So that is fine. Now in some places we are having very huge state space and we cannot have the optimal approach. So that is why we are going to suboptimal approach. Now, how can we plot this regret? It's not essential that you have to plot this regret because you are because this of computationally complex approaches. So you need not plot this regret plot. So just there was a question that how can it be useful? That is the main thing, that if we have the optimal results, we are plotting the suboptimal results, then how far is the optimal from this suboptimal? Like how much we are exploring and exploiting. This is the main overview of this. Yes, Gitika, you have raised your hand. Yes.
Yes, I had a small doubt. So In the above two graphs where there is a steeper graph that we make to decrease the regret earlier on in our exploration, exploitation, or understanding the problem. But then aren't we compromising on the regret that happens later on?
Now,
There
these two
still will be an area under the optimal graph.
This depend on the situation. If you have lesser time, you don't want to explore the more things, and you are compromising with the optimality. You have the situation in which you can compromise with the optimality. You are okay with compromising with the optimality. In that situation, it's totally fine. And there are the situations in which you are saying, okay, I want the more optimal one, so I have to explore it.
Okay,
So,
ma'am.
in that situation, I can say that that we have to go with the second one there.
Oh, madam, so in short, this gives us an idea where to stop exploring and start exploiting. The stopping point, it gives you, right?
Yes, yes. And that again, I'll say, I'll explain in detail when to stop exploring, when to start exploiting. That all things will come in detail in the next, very next lecture only. Any doubts till now? Is my screen visible?
Yes, ma'am.
Yes, ma'am.
Okay. Though I want to discuss this topic in very much detail about pack optimality. Okay, let's start. So, any idea what is pack optimality? Come on.
That we are getting within a range of the optimal arm, and we are saying that we are almost correct and also probably correct. So that means with the probability of epsilon, we are saying with the probability of 1 minus delta, we are saying that we are within epsilon of the optimal arm.
Okay, so what is the delta here? With the probability of 1 minus delta, we are saying we are epsilon. What you are saying? With the probability of 1 minus delta, you are saying that you are correct.
Within, we are within epsilon range of the optimal arm. So maybe we can differ with epsilon. We can maybe underestimate the reward with within the range of epsilon, and with the probability of delta, we may be wrong.
Okay, so what do you mean by delta here?
Delta is the probability of error.
Delta is the probability of error, or epsilon is the probability of error?
Ma'am, delta is the probability that we can get the arm wrong. Maybe it is differing a lot from the optimal arm.
It is basically the confidence. Yes. We are saying with delta confidence. Now come to epsilon. What you are saying about epsilon? Within
epsilon is the difference we are approximating it from the optimal arm. That is, we are saying it may be with epsilon, the reward may differ from the optimal arm by epsilon.
Error?
Ma'am, can we also say that the probability of error, like the difference between the estimated value and the optimal value, that it is greater than the confidence interval or epsilon, and the probability is at most delta? Like if I just take 1 there and if I calculate it, so it comes in that way, right? Like that the probability of the difference between the estimated and the true optimal reward is which is greater than epsilon is at most delta. So it can't be greater than delta.
Yes, you are correct. You both are correct. What is delta? I told you now only. What is delta?
Linear probability of our solution being correct.
Okay. Can I say it as confidence?
Yes.
Delta confidence, I'm saying that our solution is correct. Am I correct by saying this confidence is delta?
Yes, ma'am.
Okay.
Confidence is 1 minus delta.
Oh,
Yes.
I'm sorry about that. Yes, you are correct. 1 minus delta. So now can I say with 1 minus delta confidence, I can say that my solution is correct?
Yes.
Okay, now what is epsilon? You all explained. In one word, what can I say?
It's the difference between the true optimal reward and the estimated reward.
What is called true optimal reward minus
Like
estimate?
the Q star of like the A star minus
don't
Q
go
star
in
of
that
A.
analogies. Just say what is true optimal minus estimated.
So yes, error.
Can I say it as error? So now coming to the terminologies, can I say that and estimated one, they are far away from each other, epsilon, and we are saying with this much of confidence, 1 minus delta confidence?
Yes,
Yes.
ma'am.
So we'll get in more detail. Okay, first let's discuss. Do you want that I should get in detail about this pack optimality, or I should go further? Though there are lectures which are of theory about this pack optimality in the other derivations and all. I want that I should go there was a book, didn't remember the name. I'll give you the reference the next time, in which pack optimality is explained in so a very good way, and I can say that this can be useful if you are doing your research and all. It will be very useful there, this pack optimality. You can get to know that about many things, and that also I'll give you a direction like how you can achieve that. Do you want me to get in deeper to pack optimality, or you want me to proceed further, like in the next lecture I should proceed further?
Sure, ma'am, you can discuss in detail.
Madam, just one thing, this pack optimality regret, right? It is basically sizing up the regret with some confidence.
True error. Okay, you are
Yeah.
saying. Okay, can you repeat your question? You are saying that.
Previously, we discussed regret optimization. So this logically follows that, right? So how to minimize that regret within that interval of E epsilon. Oh, no, yeah. Is it, or is it discovering the right arm? Or is it, okay.
I'm saying that
what I'm saying is there any connection between regret optimality and this one, pack optimality?
I can say regret is, if you are saying in the terms of error, then we can say that the error between the true arm and the optimal, estimated arm, that is epsilon. And with that much of confidence, I can say that the error will be this much only, in this range only, basically.
Okay, man.
We'll go in more detail about the pack optimality and all those things which can be helpful for you. So you all are PhDs, MTechs, or if you'd like to discuss?
Ma'am, we are undergrad.
Pursuing MTech.
Okay. Okay, undergrads also are there. So, okay. Mostly undergrads are there. Some people are pursuing. Anyone from PhD also? Mostly undergrads are there. Actually, I need to know so that I can also teach you with that basic things. Don't want to start with the other math things so that it will okay, let's discuss. This is the discussion thing. I'll not go in detail. I'll go in detail about the map things and pack optimality, everything in detail in the next lecture. This is just, I'm going to give you the gist of that. So, greedy, epsilon greedy. First take these two map techniques. Any idea what is this and what are the difference between this?
Greedy is just being like picking the best whatever we have got every time, and epsilon greedy is being explorative with a probability of epsilon. So we are being greedy 1 minus epsilon times.
You are perfectly correct. Like we are saying that greedy is we are taking the best arm, which is giving the best reward. Epsilon greedy is like with 1 minus epsilon times I'm exploring or and epsilon times I'm exploiting basically. Can I say that?
Yes, ma'am. Yes.
Okay. Now we'll discuss more about then what will be the limitations in this epsilon greedy. Any idea? I'll get in detail in the next lecture. Don't worry about that. So what will be the what are the limitations in epsilon greedy? What are the limitations in greedy first thing before jumping to epsilon greedy?
So if I really
It does
don't
not explore enough.
yeah.
Correct. What is the limitation in epsilon greedy?
Epsilon is fixed, then even after we know what is the optimal arm, we are still exploring with epsilon probability, which we need not do.
Yes, you are absolutely correct. That now, after some time, we get to know, okay, this arm is the best one. Then also we are exploring. We need not explore after some time because we know that this is the best arm. Now, it is not initially, it is after some time when we get to know this is the best arm. Then it's the time only to exploit. So that is the limitation that we are taking the epsilon fixed one there. Though we can pool also, but this is the main.
That's what I was actually going to say, because we are anyway reducing the epsilon over time, right?
This is the thing, yes, we can do so also, that we can cool down epsilon or we can reduce the epsilon over time. But suppose we get to know, so let's not take this epsilon also. That is why we come up with this Thompson sampling and softmax and other techniques there. Or I can refer you one article there, which you can study. Wait a second. Share my screen of this. Okay, I'm unable to do this. Wait a second. Okay, you can search for Thompson sampling Stanford article. There is there. Am I audible? First thing.
Yes,
Yes,
ma'am.
ma'am.
Yes, yes.
Is my screen visible?
Yes, ma'am.
So this is the article, a tutorial on Thompson sampling. It's a good one. Okay, no need to go for this or here they have explained very well about this through this diagram, like about this dithering and all. Like I'll explain in the next lecture also. The epsilon greedy, how we came from greedy to epsilon greedy. The dithering concept is the same only. And then the Thompson sampling, in which these two algorithms, though you don't have to go in detail, I'll cover up in the next lecture. how we came up with this Thompson sampling, what is the Thompson sampling and all these things. So I gave you just so that you can refer it for the future use as well. All of you got this article? Yes. Okay. So understood today's lecture? Any doubts? Okay, let's see the comments. The greatest total possible total reward received. Will this course include projects, coding implementation? Yes, this code will include projects and coding implementation. Let's do one thing. We can do the map implementation next time. Is it okay for you guys?
Okay, ma'am.
Yes, ma'am.
So
Ma'am,
we'll do
can we do it in collab or like do we need anything else?
collab.
Okay, okay.
So let's do in like the next time the coding thing, and side by side learn what is map, and then I'll do the coding, and you can also get to know, so that you can get the hands-on practice on that.
No, and in our assignment, there was one question that what is the objective of PAC? Like, do we have to increase, decrease epsilon, or do we have to decrease delta? What would be the answer for that?
Yes, come on, no one is speaking.
I asked that in our assignment, there was a question that what is the objective of PAC? Like with
The assignments I can't solve in the class because I can solve the related questions in the class here, but not the assignment itself because it is the
yeah,
recorded.
okay.
So you can send me the question in the mail. In the next class, I can solve a related question like that because it will be recorded and the next students can also see the same assignments will be served there also.
Madam, just one suggestion based on feedback of last semester is there is a phase lag, right, between tutorial and the assignment. See, usually what happens is that first week we are actually jumping ahead with the two assignments to be completed on 8th. So what I suggest is that okay, we are not saying that you explain the assignments, but suppose next week is the assignment, or the end of this week is assignment. At least few days before, you cover the tutorial related to the assignment rather than covering the tutorial, the assignments which we already did. Okay.
Okay, you are saying me that to cover the assignments which are already done. Is it so?
No, don't cover. For example, any tutorial, what you cover is the problems related to the assignment coming next, which are with the date is still due.
Okay. So I want to know, you have covered 2 weeks or 1 week there, first thing.
I think already 2 weeks announced. 2 weeks are announced. Okay.
And 2 assignments are also done?
Yes, assignments, I think, I don't know. I think 1 week is released. Second week also, probably they will release shortly, maybe tomorrow or maybe, I think.
Assignment is released, ma'am, actually.
One is released. Two also will be released, madam. Maybe
2 is also released. Assignment for both are
2 is
released.
also
It
released.
got released yesterday only.
Okay.
Okay. So I'll speed up and I'll cover the second and third week mostly next week so that you can be aligned with the both tutorial as well as the assignment. Is it fine?
Okay, ma'am.
Yeah.
Okay. And if you have any doubt, please send me prior only so that I can cover in class. Like if you have any doubt related to the assignment, send me prior so that I can solve the related question for that.
Ma'am,
Because
we will use that email ID to send the doubts, correct?
Yes, send the doubt in the email ID. Either I'll reply there or either I'll get to the lecture also. So that the other also have the same
ma'am.
and discuss here. Any more doubts?
Ma'am, could you send, yeah, please share your email ID.
Okay, yes. Some. So I've written the chat. Is tomorrow's session different from today's? Yes, actually, he might cover some other things or some other new topics as well, or some problems also he can come up with.
Ma'am, and two more questions. Ma'am, when and where will this lecture be uploaded? Will be,
It will be uploaded on YouTube.
okay. And can we have a WhatsApp group for this course? Like, if you want to share resources or share projects and stuff.
Okay.
I just wanted to ask that. I don't know.
I also don't know actually whether I'm allowed to do that or not.
Yeah, I had the same question.
I also have the same question. Okay, so I'll tell you in the next class by asking someone. Yes, these sessions are recorded, Prashant. I'll upload in the YouTube.
Ma'am, please share the link in the NPTEL group also, if possible.
This is the YouTube channel name, Praveen Kukreja, and I'll share this lecture there.
Okay.
Today, tomorrow I'll upload it. Any other doubts? So what you are expecting, like we'll go for the coding thing, we'll go for the more of pack learning thing, the map techniques, and then comes our incremental implementation, greedy action, epsilon greedy, everything. So second week, I think there is, it's more of mathematical, if I'm not, like if I'm correct. Am I audible?
Yes, ma'am. Lots of proofs.
Okay, so we'll discuss those proofs in the next class, don't worry. Okay, thank you so much.
Thank you, ma'am.
Thank you, ma'am.
Thank you.